Hello, my name is Steve, and today we're going to use this stuff over here to build a pair of paddle controllers so we can play these Atari 2600 games over here. What are paddle controllers? Well, in general, they're a device that lets you take a rotation motion and input that into the game. And the game could turn that rotation motion into some linear motion or maybe some circular motion, depending on how it's programmed. Here are some photos showing what the original paddle controllers look like. These black paddles are Atari paddles, not to be confused with the Atari driving controller, which is cosmetically identical except for that paddle label at the bottom of the controller. We'll take a look at the driving controller in a future video. And these white paddles are Commodore paddles. They use the same plastic molds as their Atari counterparts, and apart from an internal resistor value, they're fully compatible and interchangeable between both systems. More on that later. Okay, let's take a quick look at what these 4 games have in store for us. First up is Bugs, a notoriously difficult game where you shoot at worms, lizards, and other bugs, trying to prevent them from getting to the top of the screen. Inevitably, some hard-to-shoot shape gets in your way, preventing you from getting to the bugs that are just about to reach their destination. Some freaking cruel twist on the part of your friendly developer's data age. Next is Super Breakout, the super sequel to the well-known Breakout game. Use the paddle to deflect the ball into the bricks and clear the bricks to advance to the next level. It's basically the same game as Breakout, but with different game modes like double paddle mode and a multi-ball variant. This one here is Warlords, very similar to Breakout in nature. Each player defends their citadel behind a shield of Breakout-style bricks in their corner of the screen. Striking a citadel with the ball eliminates that player from the game. This one is lots of fun, and it's one of the few simultaneous 4-player Atari 2600 games. Finally, we have Night Driver, a shadowy flight into the dangerous world of a man who does not exist. Sadly, there are no talking, turbo-boosting Trans-Ams in this game. Now, the colors match, they're pretty close, and the name is really similar, but unfortunately, that's it. In this game, you need to drive a car at nighttime and avoid several obstacles like oncoming traffic and the boundary of the road. The world winds every now and then, and that's about it. Paddles are really easy controllers to build because they don't require many components or connections. We're going to build 2 paddles using all the components you see here. We have 2 project boxes, 1 for each paddle. We have 2 1 megohm potentiometers. These are basically the dials that control and send input into the Atari. And then we have 2 knobs. These knobs fit on top of the potentiometers like so. Now these knobs might be a little too small for these boxes, so I've ordered some larger ones just as a precaution. Next we have 2 lengths of wire. It's about 2 meters or 6 feet long. And in this wire are 4 22 gauge smaller wires. Those wires will make the connections to the DB9 connector that will feed into the back of the Atari. 2 cable glands to secure each of the cables to the paddle's housing, and finally 2 momentary push buttons to implement the fire button on each of the paddles. Now the nice thing about the simplicity of this implementation is that if you have a 3D printer, you can print out the molds for the original Atari paddles, or even the molds for just the knobs that will fit on these potentiometers. All the CAD files for that is available on Thingiverse, and I'll link it to the description below. Now you might be wondering why I only have 1 of these DB9 connectors for 2 paddles, and that's because the Atari 2600 paddles used a special cable that allowed 1 of these DB9 connectors to service 2 paddles. Both of the wires would feed in here and they connect to certain pins, and the Atari knows how to interpret those signals. So we don't need 2 of these, 1 is just sufficient, and similarly for that matter, we don't have to go looking for the special cable that has the Y split into 2 different wires that go to each of the paddles. This is a much cheaper and simpler implementation. Here's a copy of the schematic we'll be working with, and it shows two paddles, one on the left, one on the right, and how we can connect those paddles to the single DB9 connector. On the left paddle, we have a push button that goes between pins 4 and 8, and the corresponding push button for the right paddle goes between pins 3 and 8. On the left side again, the potentiometer that controls the steering input goes between pins 5 and 7, and similarly for the right paddle, it goes between pins 9 and 7. Now the only tricky thing about this schematic is determining which of the two ends of the potentiometer do we hook up to pin 7. And to figure that out, we'll need to remember how a potentiometer works. So here's a potentiometer that I plan to use, and the way it's constructed is that the outer two pins are connected together by an internal resistive strip. And the value of that resistive strip will measure the rated value of this potentiometer. In this case, it's about 1 mega ohm. The middle pin is effectively what's controlled by the rotation of this knob, and it travels across the outside of the resistive strip. So what these two first pins will measure would be the distance it has traveled from this direction. So the resistance will be increasing when measured from these two pins. Conversely, the outer two pins will measure a decreasing value since it starts from the maximum and moves its way to the minimum. So the consequence to hooking up these pins incorrectly is that the controls are going to be inverted when you play your games. Now this schematic is labeled L and R, presumably for left side and right side of the potentiometer, but that doesn't really mean much because I can orient it this way and have a left and right value, and I can also orient it that way and have completely different left and right values. But the interesting thing is that the R side has an arrow that points away from the potentiometer, which leads me to think that this is the side that decreases in value. We'll verify this once we hook things up and test things with the Atari. I've gone ahead and marked up my project box with the locations of the holes I need to drill, one for the potentiometer, one for the fire button, and one for the cable gland. Now, when working with potentiometers, we will often notice that there is a small piece of metal on one of the sides of the potentiometers, and this will prevent this potentiometer from flush mounting in a box unless you drill a small hole for this. And the reason why this little piece of metal is here is to prevent the potentiometer from slipping when mounted when you try to spin it past its hard stop on either side. So I've gone ahead and marked the location of that small hole, which is about 8 millimeters from the center of where I want the potentiometer to be installed. Okay, so I'm going to start drilling into my soon-to-be paddles, and of course I'm going to use my stepper bit to drill the larger holes into this plastic so that the plastic doesn't crack and split. I have a 3/38 drill bit installed on my drill to take care of any pilot holes I need, as well as that tiny little hole that's needed for mounting the potentiometer and locking it in place. Here's what the project bot looks like with all the holes cleaned up. And I had to make this large hole just a little bit bigger to fully fit the potentiometer. It was 0.26 of an inch, so not exactly 1/4. So I just took a drill bit and I enlarged the hole ever so slightly so it would fit through and align with the smaller hole that I installed. And I dry fit the components to the box, and here's what our paddle is going to start to look like. Let's go get this thing wired up. So I prepared my cable by stripping the insulation off both ends of these wires, and I'm going to use this longer set of wires inside the cable because I want a little bit more slack when dealing with all these components over here. This length is quite suitable for the module that's going to plug into the back of the Atari. And then that got me thinking about how I want to hook up this potentiometer. I don't necessarily want to solder the wires directly onto these leads, because if I use this paddle with a Commodore 64, I'm going to find that there's going to be a sensitivity issue with this specific potentiometer. As I mentioned earlier, the Commodore 64 uses a different internal potentiometer in its implementation. It's a 500 megaohm potentiometer. So that means if you were to turn this 1 megaohm potentiometer in a Commodore 64, there'll be a significant dead zone. More than half of its rotation will just not respond in the game because the Commodore is just not looking for those resistance values. So if I ever want to swap out this potentiometer with a different valued one, I want to be able to take the cables on and off fairly quickly. And that got me thinking to what type of jacks or crimp connectors I could use to stick on the ends of this. And I found that I have these styles of connectors, which are called JST-XH connectors. They're commonly found in circuit boards where this end would mount directly into the circuit board, and this end here would have a wire and it would just plug straight in. And if we look at these JST-XH crimp connectors and try to fit them on the ends of the potentiometer leads, you'll find that they fit almost perfectly, just like that. Let's try this one down here. Yeah, that one's a better fit, so I might squeeze that end a little bit to get it to fit better. But that said, I'm going to attach these onto my wires over here, specifically the two that I'm going to connect to the potentiometer, and I'll solder those on, and then that way I'll have a more of a modular system where I can disconnect and reconnect wires and swap out potentiometers as needed. Now, when putting the paddle together, it's important to pay attention to the order in which the wire and nuts and buttons have to be assembled together. If you do something in the wrong order, you'll find that you won't be able to get things through these holes, or things won't be able to go back out through the holes and when you make mistakes. So the first thing we'll do is install the cable gland. Next, we'll thread our wire through the cable gland and make sure there is ample length through so that it doesn't get into the way of our soldering of these ends over here. Tin the ends of each wire. Solder the wires to the crimp connectors if they're not being crimped. Next, pull the cable back through the cable gland so that there's only a little bit of the insulation showing on the inside of the paddle. Then secure the cable to the cable gland. The retaining nut for my push button has a serrated end on one side. So I'll want to make sure I install this the correct way so that the serrated end points towards the inside of the box. So first I'll thread this through the wires, like so, and then I'll feed the wires through the hole in the side of the paddle box. Now my push button is ready to be soldered onto the wires. With the push button soldered to the wires, we can now secure it to the side of the paddle. Finally, we can connect the potentiometer to the remaining two wires. I've adopted the convention that the green wire will be connected to the center lead on the potentiometer. And here's what the insides of the paddles look like once their components are connected. So now it's time to make the final connections to this DB9 jack, and for that we'll review the schematic. So I put a small piece of tape on this wire to remind me that this is the right paddle's wires, and that way I won't confuse them with the left paddle's wires because they have the exact same colors. So looking at the schematic, we'll see that the green wire should go to pin 9. The green wire is connected to the center pin on both potentiometers. The red wire from both cables will go to one side of the switch, and that will go to pin 8. Pin 7 will take the white wire from both cables, that is the other connection to the potentiometer. And then pin 3 will take the black wire from the right paddle, as that is the one that's connected to the opposite side of the switch. That leaves 2 wires left on the left paddle. The black one, which also connects to the opposite side of the switch, and that will go to pin 4. And then the green wire, which goes to the center of the potentiometer, and that goes to pin 5. So the holes in these screw down terminals are large enough to fit 2 of these 22 gauge wires, so I won't need to solder them together when inserting them. However, if you notice that they are slipping out or not making a good contact, it's probably a good idea to connect them in advance with solder and then insert them and screw them down. Alright, my paddles are assembled and they're hooked up to my Atari. My Atari is also hooked up to a proper capture system. So let's give these things a test and let's see how well they do with a Super Breakout. Alright, so I believe this is the P1 paddle and it moves smoothly, but okay, look at that. The controls are inverted. If I turn the controls clockwise, you'll notice that the paddle moves to the left, and when I turn them counterclockwise, the paddle moves to the right. So that should be the other way around, and fortunately that's a very easy thing to fix because I didn't solder the components on the back, and let's take care of that right now. So all that we need to do is take this white wire and move it to the other terminal on the potentiometer. Right there. And that should do it. Let's give it a quick test before we put things back together again. I'm going to turn clockwise. And the on-screen paddle moves clockwise. If I turn counterclockwise, it moves to the left. So this looks pretty good. Controls are really smooth. And while we're at it, let's fix the other paddle because it probably has the same issue. Put this back together again. All right, we're good to go. Let's play some Breakout. So I'll put this on, well, let's pick an interesting mode. How about double paddle with those googly eyes? That looks interesting. Let's try this one out. All right, here we go. So far, so good. This is pretty smooth. I like it. Now, the one thing you might notice, and this is somewhat expected, that the range of motion that the game is using on the paddle is actually really small. So if you pay attention to the line, the indicator that's on the paddle, you'll notice I'm not using the full range or anywhere close to the 300 or 270 degrees rotation that the potentiometer has. And that's mainly because the Atari is only looking at a very small range of resistance to determine where to move the on-screen paddle when I rotate the control. So this might be okay for some people, and it might not be okay for others. And the easiest way to get around that is to basically change the potentiometer that's inside, perhaps using the Commodore potentiometer that has a value of 500K, which is half of the 1 mega ohm the potentiometer that's in there, and that will increase the range substantially, maybe twofold. Let's find out how much range we're actually using here. So I'm going to put this all the way to the right, and so the line indicator is right there. And if I move it all the way to the left, it's somewhere over here. So that looks like it's about 45 degrees, not much. You'll get of course, you'll get a better range with a smaller value, but the caveat there is you have to make sure that the game system is actually reading the values that the potentiometer can put out. So let's say, hypothetically, that it's looking for ranges between 700K and 900K. If you put a 500K potentiometer in here, then it just will not work because it cannot produce those values. So you'll have to do a little bit of testing and figure out which potentiometers work best. I'll probably make a video about that because I think there's some good technical insight in how we can go about producing an optimal controller that you can maybe tune or figure out the best range of motion. Okay, so let's try Warlords, as that requires some button presses, and that'll give us a chance to test both of these paddles simultaneously. Okay, it's currently on 4-player mode. I'll put it on 2-player mode. And the default mode of operation for Warlords is what's called the catch mode. So if you hold the button down and the ball hits your paddle or your character on the screen, you will catch it. And then you'll be able to release the button and fire the ball back at a particular target. So let's give this a go. All right. So I'm in the top corner on the left side, and I'm the yellow guy, and I'm going to try and catch the ball, and I'm not very good at this. There we go. Okay, so I've caught the ball, and I'm holding the button down, so this controller is working very well. Let's release it, I don't know, at the second player, and go like that. All right. So I will now switch to using the other paddle, which will control the second player, and here we go. This is also really smooth. There's no jitter, which is desirable for these types of controllers. I'm going to hold the button down, and I'm going to try and catch the ball if it ever comes my way. There. And I got it. Okay, you can kind of see that it's on the left corner of my character, and I'm holding the button down so I can release it at any given time. And there we go. Okay, so both of these paddles are working exceptionally well. I really like the way these turned out. Perfect. So that will conclude another controller video, and I hope you found this information useful. We've got one more controller to tackle, and that's the Atari driving controller, which looks a lot like this one, but it's somewhat different in functionality, which we'll explore in that video. Thanks for watching. Hope to see you soon.